Thank you very much. Sorry, my students who did most of the work could not be here. As you've maybe heard in the news, things are not great in the United States. They couldn't make it, but it's my pleasure to be here and talk about their work. Oh, well, there we go. All right, so the topic of this talk is pretty sort of, in some sense, quite sort of cut and dry and fairly narrow, which is that we're looking at a certain point in the design space where we're taking a sort of a meta ML-like language that's got quote and splice, or quote and unquote, or quasi-quote, however you want to talk about it. And then we're combining in the notion of gradual typing. Okay? And though in particular for this one, we're looking at a situation where the metaprograms are gradually typed and the generated code is statically typed. Okay, and part of this has to do with our collaborators from industry, where you're generating maybe like SQL or something, and you really want to have more guarantees about that generated code. So you want that to be statically typed, but maybe the code that's doing the generation is maybe like Python. And so that's going to be more likely to be gradually typed. Okay, so there hasn't been that much research on mixing gradual typing and this kind of metaprogramming. Actually, concurrent to the work that we were doing here, there's a paper in GPCE this year that also is sort of a first steps. And I'm going to say just a few words comparing what we did to what they did. A lot of it's very, very similar, and there's just sort of one little design decision that's different. And so, yeah, the whole point here is to talk about, like, well, how do we deal with the interaction between gradual typing and metaprogramming? How do we put the two together? Okay, and just to kind of give a high-level overview of like the different artifacts in the system that we're building, is you've got your source language where you write your metaprograms, and that's this MetaGTLC. And then the semantics of that, as usual, we compile down to a lower level language. Down at this level, this is CC is for cast calculus. So this language has lots of implicit conversions because it's gradually typed, and there's lots of dynamic, sort of implicit dynamic checking happening. Down here, it's all very explicit. And then you run your metaprogram, and that's going to generate essentially simply typed lambda calculus. And then you can run and then this is completely standard running the generated code. Okay, so that's kind of that's the setup. So just diving in here, the syntax of this MetaGTLC. First off, we have the types of the meta language. You've got base types, you've got function types, so that's the usual. Stuff that's just black is like STLC stuff, okay? The blue things are going to be your typical things you get from MetaML, okay? Your typical metaprogramming features. So this is like this is a code type here. And then the star here, that's the any type from gradual typing, or the unknown type. And this is saying you don't know at compile time what type the thing is actually.
So what's this thing on the left that looks like an eye without a dot?
Oh, that's your just base types like that and bool. It's ranging over that. So now what's a little bit interesting here with the types of the object code. So here we have our STLC types. This is just, you've just got functions and base types. And so what you have for your code, well, it's got just STLC stuff in there. So you're not going to have mixtures of the star all over the place. Instead, you can only have it sort of at the top level. So we're really sort of in the meta system, we want to be able to say you have code of unknown type. And you can say that with this grammar, but you can't say I have code of function type that takes star to something, right? Because this is the STLC inside of our code, right? So it's statically typed there. Okay, so then our metaprograms, you've got your usual lambda calculus plus quote. And then for your object code, you've got lambda calculus plus splice. So that's just the usual thing. here we've got type annotation, and that's hinting that we're going to be doing a bidirectional type system. And we were sort of forced into that for a very technical reason that I'll get into, okay? We didn't start out saying we were going to do bidirectional, but we sort of ended up there. Okay, so we're basically just marrying, the stuff you need for metaprogramming with the stuff you need for gradual typing. Okay, now one point I should make about this language setup here is that this is super simple. Okay, this is like we're taking first baby steps towards integrating gradual and metaprogramming. We've left out eval, and we've left out things like mutable references. And so with this little language, you don't have to worry about this thorny problem called scope extrusion. Okay, so that just can't happen in this little language. Okay, we're currently working on what happens if you do add those things, and then things get a lot more complicated and a lot more fun. Okay, so like I said, so this was our sort of our source language, and then we're gonna compile this down to this CAS calculus. Okay, and this is the CAS calculus is sort of where we're really going to be like spending our time, like really thinking about the runtime semantics, okay, what's happening. And in this language, you now express all your implicit CAS explicitly, okay, with this is a term M with a cast on it. Casts are explained through this sort of combinator language called coercions. This is a really nice little language that Hengline developed back in the 90s. And it turns out that when you're trying to design new gradually typed things, it's really helpful to do it using coercions because they sort of like give you less freedom and sort of steer you towards the right thing, okay? And so the red stuff is all standard, coercion calculus stuff. But then the green stuff is the new stuff you need for the interactions between gradual typing and metaprogramming. And so what we have here is it's a cast on that's under a quote. Okay. So actually, let me show you the typing rule for that. It's this one right here. Okay. So if you're trying to cast from one quoted type to one code type to another code type, you can do that, and as long as you can cast from whatever the underlying type is. Okay. And it wasn't hard for us to come up with this rule here because it's a lot like the function rule, except it's easier, right? With the if you just look at the domain here, how you cast the return value of a function, that's what that's doing, and you don't even have to worry about the contravariance over here. So this is pretty simple to come up with. There wasn't a lot of freedom there. So these coercions. So this is Henglin's reduction system for this little combinator language. Okay, so for example, if you have an identity coercion, then that just goes away, right? It's identity. If you have these bangs and question marks, the bangs are injections, so you're going from some type to the unknown type, and then the question marks are projections, so you're going from the unknown type to like integer. Okay. And the question mark ones are the ones that could fail at runtime. You should think of those as like procedure, or things like that in bracket. Like you're saying, are you a function or are you a number? And the L there is the blame label. So it's like if this projection fails, you want to give an error message, and you're gonna be able to like point back to some line number in your program that's being stored in that information, right? So like this is a check that succeeds. This is a check that fails, if A and B are not equal. Okay. And so the cool thing, one of the cool things here is that most of this is just red, like standard coercion calculus stuff. We didn't have to make very many changes. We just basically had to say, how do you deal with this quoted coercion? Okay. And this first rule here is a distributivity rule. Just says, how does quote distribute with sequencing, and it's just you just push it inside, right? Which is quite similar to what we do for function types already. So that didn't require that much thought either. And then this one This is oftentimes you have got these rules for bubbling up identity, that you're discovering that you've got an identity cast. And you start, like, here's the one for functions. If you have a function cast that's not doing anything to the input or the output, that's just an identity. And same for, so we just had to do the same thing for coded types. So that was easy. And then once you've done that work for the coercions, then here's the actual reduction rules for the actual lambda this lambda calculus with casts and coercion. Okay. And the cool thing here, again, is that most of this stuff is just standard that had nothing to do with the intersection of the meta and the gradual. So this is all your just standard gradual, what you need from a coercion calculus in terms of reduction rules. And then, these are your standard reduction rules for splice and quote. Of course, you need to be able to reduce under quote to get to your splices. And if you've got a splice, you need to reduce under that, reduce whatever meta stuff needs to happen under splice. And then finally, you've got splice quote. That just, they cancel out. Right? So that's all standard. The only thing we had to add was just that what happens if you have a cast failure in some metaprogram that's inside of a splice, right? And obviously you want to propagate that exception up to the top, right? And so we just had this rule for propagating our exceptions up through splices and quotes. One thing I'm not showing you here is there's a lot more like congruence rule kind of stuff that I'm not showing. So. All right, so here's where we want to do sort of this, there's like this one design decision about what's going on differently in our paper versus the Weixi and come up Miala paper in Gypsy 2005. So their reduction rule for what happens when you have a coercion on a quote is they push the coercion into, through the quote, okay? And so this reduction rule follows the traditional pattern that you'd see for other things in terms of other kind of introduction forms like lambda. So like one of the ways, like when you cast a lambda, you apply a function cast to a lambda, you could do like an eta expansion of your lambda and and inside of that, you're going to be casting the domain and codomain. So this is a similar kind of thing like that. We're sort of pushing this coercion underneath. However, what this rule does, it's basically saying we've got a cast that was happening during meta evaluation. I mean, when you push it under the quote, it's now going to delay the cast to maybe fail, but not at meta evaluation time, but at the runtime of your code that you're generating. Okay. And so that's something we didn't want to do that delay. And we want to have our errors, like if we have a cast error, we want to know about it during meta evaluation and not when we run the generated code. So that's why we steered away from that rule. Also, this reduction rule sort of assumes that your object language that you're dealing with inside here is gradually typed, that you can have casts in that language. But if you recall, our object language is the STLC. So you can't have casts in there, okay? And so it doesn't really make sense to have a cast showing up inside of a quoted term. Okay, so that's another reason why we sort of ended up with a different design. And so maybe it's a little bit hard to see like why, like where's the lack of this rule over here? So like, let's say like one of these V's could have been like a quoted entity, right? A piece of code. And you'll see there's no reduction rule. There's no one specific to that. Like we don't have this actual reduction rule in our system, right? But what's happening instead? You could, like this C here could be like a quoted, coercion with more coercions inside of it, right? And so here we're saying, oh, do coercion reductions inside of there, okay? And then, that's going to trigger the stuff from this page, right? So maybe you have, stuff like that going on where you're composing those and so on, okay? And maybe your casts on your quote go to ID and then, then they just go away. Or maybe they trigger, blame. Okay, and then the blame gets propagated up. Okay, so all of that kind of stuff can happen either through here, and then it finally turns into an ID, and then it just goes away, or it goes to blame gets propagated up, and then your whole program goes to an exception. So we basically just never, that those casts involving quotes either always turn into IDs or they always turn into blame. It's sort of the at the end of the day. So that's kind of the story there. Okay, so we've now established the source language and then the cast calculus. And then now the question is like, well, how do we compile the one to the other? Okay. And this compilation is type directed. So here we're sort of seeing both the type system of the source language. So this is the gradual type system, and we're also seeing how do you compile down to the cast calculus. Okay, so there's sort of two things going on. Again, the things in black are just your normal, what you'd expect to see if you were just STLC. And then the red things are standard for gradual typing. So like how you compile function application is just completely standard. And then like how you compile quote, this is going to be completely standard. So now we're going to get into this one other sort of main point of this talk, which is why did we do bidirectional? Okay. And you'll notice that, so for this compilation here is for the meta program, the meta level, okay, which we're not doing bidirectional here, okay? But we are going to do bidirectional for the objects. So once you're inside of a quote and you're compiling that code, that's going to be bidirectional, okay? And so the reason is over here in green, okay? Which is that we're looking at a splice here, okay? And we and let's say, and we can compile that the meta code, the meta program, to M prime has type A, and then that type A could be something like dynamic, like the unknown type. That type A could be something like code of dynamic, okay, code of unknown. Whereas the context here is STLC, so it's got to be a fully static type. Okay, so it's likely that we're going to need to do a cast at the boundary here between our gradually typed world and our statically typed world. Okay, and the fact that we've got this consistency check here, like, okay, that's the implicit check that would be happening in the type system. And then for the runtime, we're going to need to generate an actual coercion that'll do the runtime work of that cast. Okay. And this cast needs to live in the meta program inside the splice, right? We can't do the cast in the object code, that stuff's statically typed. So we're going to need it inside of the meta code here. To figure out this cast, we need to know the target type of what we're casting to, okay? That target type of where we're casting to is whatever's the static type expected in the context of the splice. So we need to know, like, above the splice, in the AST, like what the code above us, that STLC code above us, what is it expecting, okay? And so this means we need to be doing bidirectional in checking mode. Okay, so we get the target type T from being in checking mode. Okay, so that's why we had to go bidirectional. We sort of got to this splice rule. We're like, how on earth do we insert this cast? We need T. Okay, fine. We'll go bidirectional with that. Okay, so that's one of the other main points is that rule there. Yeah, if we didn't go bidirectional, I wouldn't know how to do this. I mean, maybe there's other ways to do it, but this is what worked for us. Okay, so this is now going into the, how do you generate those coercions, right? The coercion calculus. And so almost all of this stuff is completely standard. And this is like, oh, if you're going from some type to star, that's an injection. If you're going from star to some other type, that's a projection. Okay, so that's all normal stuff. We mostly just needed to add rules for dealing with quoted, if you're casting between quoted types. Okay, and that's where this quoted coercion comes in. Okay. This was pretty straightforward to deal with. Okay, so does this design deliver on what we're hoping for? The basic thing we were hoping for is type safety. And so what this says is, okay, you've got a metaprogram that says, I've got type quote of, code type of type A. And if I do a compilation and compile that down to N, so this is going to be in our cast calculus intermediate language. Then, as usual, we've got three options. It either can run, and then we're going to produce code of the expected type. Oops. T. Oh, you know what? This T should have been, actually, this A should have been a T. I'm sorry. And then, or you might get an exception, like you've got, this is gradual typing. So just like dynamically typed languages, sometimes you can throw exceptions. And then you might also have divergence as a possibility. And so that's kind of the usual type safety proof that you'd expect. We did formalize all this in Agda, and the proof of type safety is in Agda. Okay, so to conclude, metaprogramming and gradual typing can be integrated. And the main thing you want to do is add a quote coercion. Okay. So the other main point is this thing about, at that splice, at that point where you need to do the splice, you may very well need to add a cast at the place where you're doing a splice. And that's why we needed the bidirectional typing, so we know where does that cast go into, to make sure that we could put the cast in the meta part of the program. Okay? And if you're, like to look at this in more depth, here's a link to the GitHub repo where we have all the Agda code for that. All right, so with that, stop just a couple minutes early here. Plenty of time for questions. Yeah.
Can you let me say that bidirectional typing is a limitation or is bad? Like what's the problem?
I wouldn't, nowadays I like bidirectional typing, and I would like if I'm going to go design a new language, I would make it bidirectional anyways. But that's my opinion. Like, there's probably a lot of other people who'd be like, no, I want something else. So that's, I'm just, if you said, oh, I want to do Hindley-Milner, I'm not sure how I would do that for this system. And maybe that's a paper being, that needs to be written as how to do that. So yeah, it kind of depends on your perspective, I suppose.
But before the next question, let's thank the speaker.
So you said that this is like the standard way of doing this kind of rule where you put the conversions in there. So there was like this previous standard rule of like to drop it sort of inside of the quotation so you have it like in the next stage.
Yeah, okay.
And then you have this alternate way of doing it that lets you catch it earlier.
Right.
That, like on the face of it, that sounds strictly better.
Yeah.
Is there some advantage to the older way of working it? Like, why would I prefer this over the way you said it?
So actually, this isn't older per se. This is like concurrent. Like so
Oh.
this is like, we actually, in fact, we didn't know about each other until we noticed each other's publications coming out. We're like, oh hey, and so, but this rule is the kind of like, I mean, I don't know. I should ask Higuchi how he came up with the rule. Like, I don't literally know how he came up with that rule, but this rule looks like a lot of the rules that you would see for like lambda, or for other introduction for like pairs. Like, how would you push a coercion through a pair? It would look like this.
It's like pragmatically, like resulting language, like catching errors earlier, like it seems better to catch.
Yeah, absolutely. So I don't know how much they thought about like this trade-off. Like maybe they didn't think about it, or maybe they did, I don't know. But to me, this was like almost like a deal breaker, where it's like, no, we don't want to do that.
And then another kind of sort of somewhat related question. So you were saying like in the type safety proof, like what are the things that can happen?
Yeah.
But like there's one, isn't there like maybe it's captured the term, but the things of like there isn't enough type information in the metaprogramming to get a fully typed final, like if you're going down to a fully typed language, you can imagine it's like you can have any type applications anywhere and like you can't get it. So like is that divergence? Like what's that? Is it like
No, we've sort of set things up static in terms of, we've set things up sort of syntactically and whatnot, where the quoted stuff has enough annotations and things on it that it'll definitely be fully checked. And I mean, I didn't even write like I didn't say anything about running this code, but this code here is STLC, so you just use the normal STLC type safety proof to know that you will not get any errors whatsoever. Like you won't even see blaming kind of errors. This one will either go to something of type T or it'll diverge.
That like in the like real world context you're thinking of, applying this to like someone like tracking together something in Python that's gonna like evaluate down to something like statically typed language.
Yeah.
Does the error case I'm talking about exist there? Where like you just didn't, it's a graduate cases and they just didn't write enough down? No.
No, in that setting too, it's that our type checker, our gradual type checker is like being fully static about the coded bits. So it's like catching a bunch of errors really statically there. Ron. Uh-huh. Yes, that's wonderfully said. Yeah, because whenever any actual coded term you have is going to have its type, like if you're thinking like canonical forms or something, its type is going to be quote of like int or quote of like int arrow int. It's going to be a fully static type. But that quoted thing could be flowing around in this gradual metaprogram, getting passed to a function that was expecting something of quote star. So you lose that information as it's passing around, but then maybe later on it's passed to something that says I'm expecting quote of int, and you've got a projection happening there. I think as soon as you make that step, I think you're sort of like saying, I want gradual typing in my object code. Okay, I mean, if you maybe like writing some example, we could look at some examples of what you have in mind, and then that would become clear. And like, I mean, because the main thing you do with code is you splice it into other code, right? And at the moment when you splice, we're going to make sure that it's like fully statically matching up. Exactly. That basically got a question.
The only things you can do with the star, like
Yeah,
That's one.
yeah.
And if there is more precise type inside. To see what.
And the way we're doing the coercions and stuff in the compilation is that as you're doing that splice, the actual type of the thing being spliced has to be fully static again. So maybe you have some projections happening right there that are getting you back to fully static.
Yes, I was thinking like you have 3 segments, you got a program that like, I don't need to know what the place of the person, I really want to participate in it.
Oh, okay,
So
that, yeah, I
we
think,
should take the rest offline.
Yeah.
Sorry.
yeah,
Okay.
I'm digging what you're saying, I get it, yeah.
Let's thank the speaker again.